Today, I'd like to introduce an important problem more and more businesses are being flung headfirst into within the 21st century. Whether you know a little bit about how artificial intelligence is computed in the data center, or quite a bit, this talk will help business and technical sides alike understand why GPUs have become the front and center choice for accelerating AI and data science workloads in organizations small to large, the major issues they face in garnering financial efficiency, and how the approaches the GPU vendor ecosystems of today aim best to solve them. For each side of the organizational equation, the conversation surrounding AI hardware differs significantly. Where business's responsibility lies within the ultimate purchase of infrastructure, it must be done with adequate considerations to the current picture of organization and the value of the AI data it generates. Can I afford to? Can I afford not to? Is the common questions that must be asked when assessing the positive and negative impacts new hardware and infrastructure will have on the progression of internal innovation and value adding. Understanding the landscape of AI hardware itself, as well as how to best approach the problem of enhancing financial gain while reducing financial burden, are groundworks this talk will aim to deliver. For the technical owners, working hand in hand with your business leaders requires a pivotal understanding of not only the variety of AI workloads your infrastructure deploys, but the crucial considerations each type demands of the infrastructure that deploys it. Fail to do so and suffer the financial repercussions of underutilizing some of the most expensive hardware your organization will buy. Far worse, if without an understanding of the maturity AI teams and products currently sit at within the organization, the more technically and possibly financially burdening issue of adopting incorrect hardware and architecture is certainly possible. To understand the playing field of artificial intelligence hardware, we must first understand how we got here, why AI has become such a crucial technology adoption for most businesses. Historically, data compute has been about small amounts of data in, large amounts of data out. With the major explosion of IoT traffic, data volume, and worldwide data warehousing, we find ourselves in the exact opposite school of processing today. It's now common to see even relatively generic artificial intelligence neural networks handle tens to hundreds of billions of parameters within their calculations. The flip to massive generic data in, small, precise data out is driven by the advent and adoption of neural networks and massively parallelized data analyzations to scale. Legacy compute through CPU, a platform efficient primarily for serialized processes, now fundamentally fails to keep up with the extreme parallelization these workloads demand. To continue to match pace, enterprise data centers have set their sights on rapidly adopting GPUs, the key and critical hardware designed for accelerating the key parallelizable aspects of AI and data science workloads. So how fast are we really growing data usage? And how ready are the businesses for the compute-heavy analysis it drives today, let alone tomorrow? Well, most are prepared for today, yet woefully underprepared for tomorrow. Worldwide data transacted is expected to reach more than double in present-day volume by 2024 to a staggering 149 zettabytes. This exponential scaling is more than likely to continue far beyond 2024, despite having many businesses swamped today with seemingly unmanageable volumes of information. There has to be a solution. AI. Parallelizing information compute at scales matching the data flow through your organization with near-human decision-making enables massive insight generation that propels profits and generates valuable intellectual property for organizations with mature AI solutions. But what is your current level of AI maturity? Perhaps you haven't started, or perhaps you're in an organization with AI IP, a wide variety of compute workloads, and a mature development ecosystem. Regardless, understanding how to quantify AI maturity within your organization's development and infrastructure ecosystems will enable you to validate your own AI infrastructure readiness for the workloads of today and tomorrow. To start that discussion, let's break down some of the fundamentals crucial to understanding AI infrastructure. What are the possible AI workloads, and which of them make up the majority of your AI ecosystem? Primarily, there exists three types of accelerable work in neural network development: building, training, and inferencing. Building, of course, is the trial and error phase of model development. Short runtime, small batch sizes, driver, library, and code mistakes characterize the majority of this process. While these tasks actually require minuscule amounts of compute, as developers only really care if their code runs. They historically are forced to occupy the entirety of the GPU regardless. Training, of course, is the bread and butter of neural network development. Long run times, possibly spanning multiple days, larger batch sizes, and larger model sizes characterize the majority of training jobs. Maturity of applications are most often defined by the length of training time and or the complexity of the model being trained. Inference is the final step to an AI product. After optimization, what's left is a condensed model designed to make the final intelligent decisions on small, varied batch data that it processes. While holding minuscule compute demand compared to training, inferencing still remains one of the most important aspects of AI model development, as it alone generates the end value that the entire AI product hopes to deliver. Measuring the value of this data will help organizations prioritize the decision-making to best affect the star profit-driving models they own. So why are GPUs actually good at speeding up AI? Here's a great analogy. If you consider a CPU a Maserati, a GPU can be considered a big truck. The Maserati can fetch small amounts of packages from RAM quite quickly, whereas the big truck is slower, but can fetch massive amounts of memory in one turn. We still need the Maserati to do the lightning fast prep work of moving data around and running our framework. Yet the big truck is the real superstar of the operation, with its utter brutish power enabling the bulk calculations of AI to occur at unparalleled speeds. It's this hand-in-hand partnership between these two differing processing units that's enabled AI acceleration in the 10 to 40x magnitudes. For those of you who aren't new to AI talks, this is a slide that you've likely seen a million times, so forgive me. But for those of you who are new, this is undoubtedly important. Moore's law frankly serves as humanity's guideline for keeping up with its own data evolution. The core concept is an empirical relation between the historical production and experience, related to the fact that raw processing power of silicon chips will double roughly 1 to 2 years. With more than 3 decades past the inception of original processing chips, we see that CPUs have begun to plateau in that relationship, failing to meet the historical pattern. GPUs, however, have quickly picked up this trend, doubling just as expected in Moore's law. Where one processor architecture falters, another is right there to pick up where it left off. Yet, all of this compute is only useful as how you use it, or quite frankly, how little you waste of it, is so important. So what are the primary challenges? Measuring the percentage of each type of workload that makes up the total AI development flow in your organization will not only help you define your ecosystem maturity, as inference heavy and mature to training heavy and experimental, but will also enable focused infrastructure design, allowing you to capture the predominant utilization fall-off mixing workloads often brings. Let's review some of the key differences in the workload characteristics we saw earlier. Having the remarkably short burst and low utilization inference and build jobs battle for valuable resources that the high utilization, long burst training jobs can hog, can often leave expensive AI developers idle as they wait for compute to debug and data collect. The opposite obviously also applies to training jobs waiting on inference and build jobs. Having teams at various ends of the AI product development cycle can lead to a constant push and pull of GPU resources. Teams have faced a dilemma of either offloading build and inference jobs to slower CPU compute servers to ensure that utilization is focused to training workloads, or faced low utilization repercussions. Certainly not optimal. Data gravity, ecosystem maturity, and AI product value may help you determine between an on-demand public cloud, on-premises private cloud, or hybrid cloud solution for your organization. Finding the inflection point that data I/O costs outweigh on-demand cost-saving potential will vary from company to company, but should still serve as a continuing tracking point for all who develop and deploy AI today. For being one of the most expensive pieces of hardware you will buy, using it inefficiently can be a massive cost to financial drain in not only initial CapEx, but continuing operational expense. GPUs require power, lots of power, and even under minor or idle load, they can massively suck up your energy costs. Even training a single GPT-2 AI model can cost anywhere between $12,000 to $43,000 US in just raw energy cost. GPUs can use as much as 66% of their total possible power draw at only 10% load. As most companies will need to run their GPUs under various load types, your ability to optimize utilization of hardware under dynamic conditions may make or break the financial equation of profitability. It is critical to approach the problem of compute utilization with the solution of consolidating as many workloads as possible within the same GPU frame, without, of course, unacceptable detriment to the workloads themselves. GPUs, much like CPUs in the era of pre-virtualization, face an average utilization of only 15 to 25%. So how are we solving this problem for GPUs in enterprise? Let's take a look at some of the old and new ways of going about this. Well, why not virtualize GPU compute like we did with CPUs in the 90s? Well, GPU and independent software vendors have, and they continue to do so in better ways, iteration by iteration. But GPUs, crucially, are not designed like CPUs, thus we cannot expect the same results. The primary method for the better part of a decade has been to utilize the multiprocessing server technology for CUDA workloads NVIDIA cards have supported since 2010. MPS, however, has come a long way since 2010. Based off of optimizing the message passing interface workloads that AI applications at a kernel level are made up of, MPS attempts to efficiently remove the context switching that quasi-shared MPI parallel technology introduced. While succeeding in allowing multiple applications to utilize the same GPU via compute slicing the processing cycles, MPS is not without its own inherent flaws. As kernel and memcopy operations from different processes overlap on the GPU, maximal load of one resource-hungry process can inhibit the operation of another with added latency as they battle for access to memory bandwidth and low-level hardware operations. Even more troubling, MPS is not fault-tolerant. An error or fatal flaws in one MPS slice will reflect across all MPS slices, resulting in either confusing logs or worse, healthy adjacent processes being killed. With all the aforementioned, there is certainly much to be desired. Building on MPS, the virtual GPU framework available through NVIDIA's Virtual Compute Center infrastructure layer enables the slicing of MPS instances or full physical GPUs into VMs allocatable in GPU slices. These vGPUs are allowed to be attached in fractional physical, multiple vGPU to single VM sources, or just bare metal performance utilization within your environments. Well, this sounds pretty good, right? Not so much. It still runs MPS as its backbone. We all face the same latency, load, and fault tolerance issues that MPS holds, albeit with far more enterprise-friendly platforms. Critical AI applications may shy away from vGPU infrastructure for exactly those reasons, as multi-day training jobs would endure an elevated risk to sudden shifts of compute latency vGPU allocations may have. Moreover, the largest AI training workloads may require multiple GPUs. One must consider the distance of those vGPU allocations as crucial considerations in architecture. If your application is large enough to require multiple GPUs worth of memory to hold your model, the communication transfer latency between cards is critical. vCompute Center bases no affinity to co-locating processes utilizing multiple GPUs, instead scheduling across what is available, not considering within-box NVLink potential or box-to-box transfer speeds. The farther away your compute model is from the CPU driver, the more costly data gravity becomes. With MPS and vGPU laying crucial groundwork for multitasking workloads on physical GPU instances, it's no wonder vendor solutions have come out of the woodwork to attempt to do better. RunAI is a fantastic example, a Kubernetes-based scheduler leveraging MPS for preemptible workloads in a fault-aware manner. Allowing your enterprise to designate guaranteed on-demand compute resources for the most important development teams allows for idle resources to be engaged by varying maturities of AI product, with the least important gracefully losing resources for their workloads when the most important demand their full quota. If you're thinking about a segmented infrastructure for crucial compute, RunAI is quickly shaping up to be a star player in the prioritized multi-tenant environment space. While impressive, RunAI does lack in handling the all-too-important problem of scheduling affinity, meaning that multi-GPU resources can stretch multiple physical nodes, regardless of request. Data gravity is no joke. While within-box communications with GPUs can run at upwards of 600 gigabytes per second with NVLink, between-box communications still remain at a height threshold of 200 gigabytes per second, even with the latest Mellanox InfiniBand network hardware. The size of your largest models and datasets must be accounted for to understand potential training latency of perhaps your most important products. Altair takes a similar approach, yet offers far more granular control and compute splitting, and picks up where RunAI falters in providing the hardware affinity required for the most massive AI and HPC applications. While manual configuration heavy, the ability to stretch workloads across multiple GPU nodes and physical GPU slices, consolidating compute requests as close to the originating CPU as possible, can lead to lower latency and higher stability that some applications may require. Altair, a pro in the computational fluid dynamics simulation space, already knows about the importance of data gravity for the most important and demanding workloads possible. And while lacking the preemptive scheduling and dynamic fault handling that RunAI offers, any enterprise on a goal to push the threshold of AI and HPC development with expert infrastructure and development staff should take a strong consideration to the offering that Altair brings. The concept of splitting many low compute necessity inference, build, and small training model workloads across the same GPU in a completely hardware isolated manner is one that GPU hardware providers have been striving to reach for years. Nvidia has only recently released their own solution to this problem, coined the multi-instance GPU, MIG. Available on the new Nvidia A100 GPU series, their fastest enterprise GPU to date. It allows for 7 discrete GPU slices armed with their own memory, cache, and compute cores, fulfilling each with its own fully fault-tolerant, low latency, and predictable quality of service partitions. No longer do you have to worry about designing separated infrastructure for your most valuable teams. True multi-tenant environments can now exist with MIG without lower priority experimentation, afflicting higher priority development, training, and inference. MIG is pairable with Linux enterprise operating systems and with vCompute Center NVIDIA offerings, allowing platform teams to integrate MIG instances as hardware or vGPU attachments to container and VM environments alike. Whether you choose to accelerate your Kubernetes variant or pass through a MIG instance to an OS with a full development environment, rest assured that you'll be able to meet the various demands that your enterprise introduces. For applications that do not need to leverage NVLink for multiple GPU training, MIG stands to be one of the best infrastructure choices for enabling massively multi-tenant enterprise to accelerate AI development growth and reduce underutilization of GPU assets. While MIG is a leap in the right direction, it still suffers from the time-old tale of focused implementation. The only AI ops platform to date serving MIG support through workload-aware scheduling is Converge.io, a relatively new AI partner to NVIDIA. As MIG has become only available as of May 2020, it will not be surprising to see classical platforms such as Altair and Slurm add functionality in the near future. I'd like to quickly touch on some of the outlier cases of AI, data science, and high-performance computing. There's been 2 primary schools of thought at this edge: virtualizing or replacing the PCIe fabric entirely to allow GPUs to be attached to any aspect of your data center regardless of location, and field programmable gate arrays, or FPGAs. While folks like Gig.io and Liquid have focused on attempting to virtualize the entire PCIe fabric, being able to hold signal integrity across distance and cache coherency between devices is incredibly different difficult. Intel has gone as far as to replace the entirety of the fabric itself with their CXL and Gen Z offerings, yet they still face the same issues of signal integrity, albeit with improved cache coherency. Field programmable gate arrays are a whole different ballpark. Incredibly powerful, yet utterly difficult to manage, that can easily 10x the infrastructure architecture complexity, but exceed GPUs in both compute potential and power efficiency. Only the most experienced product and infrastructure ecosystem should be eyeing these solutions, as a cohesive view of your workload variants and DevOps skill will allow you to determine if these are worth the hassle. Now, I've posed a couple of questions for the business leaders and technical owners of today. While I won't go into detail, I will make sure that this presentation is available after this conference so that you may read through, and if you are currently tackling this decision-making process, I hope that this aids you in finding the right solution.
What should business owners do if they are facing the GPU apocalypse right now?
Well, for the GPU apocalypse, face to the public cloud, right? Folks like AWS, Azure, GCP have all gone through the effort of acquiring massive amounts of GPUs in their stead. Now, when it comes to enterprise GPU compute, if you're an organization with the wallet and enough sway, folks like Nvidia will always provide enterprise GPUs to you, and most afflicted is the consumer side of that conversation, not the enterprise side. However, right, if you are small or a startup, you should look to on-demand cloud compute.
I was reading that people are now buying up like storage devices, like external hard drives now, as a way to somehow store the cryptocurrency, or there's like a new way of mining some weird crypto. I don't know, completely off topic, but I know that GPUs are certainly very...
primary driver, right?
Yeah, totally.
And it's exactly for some of the aspects that I talked about in this talk, right? Their ability to do those matrix floating point operations at massive speeds enable them to, do those logical calculation blocks or mining that most cryptocurrencies require.
Wondering if you can elaborate on the scenario at RBC where you hit GPU infrastructure issues and how you address that.
So I won't be able to talk about exactly how we've architected it, but I can at least give you a pretty good idea of the problems that we face, and based on some of the content of this talk, how we might have solved them. We're massively multi-tenant, right? The issue of having varying degrees of AI team maturity means that you want to enable developers that may have never run an AI model in their life to have access to GPU compute. And the teams and Adam, I know that you had them on a few months ago, like our Borealis AI division that is tailored to doing real-time analysis of market data and real-time training, will ultimately need those resources as well. So how do you handle that problem across both the amateur and the expert, right? Now, some of those compute splitting capabilities that I talked about earlier certainly come into play. And while we've made very, organization-specific considerations to exactly how we've implemented that, I can certainly tell you that we're leveraging some of that on-card split and across multi-card compute cycling.